In section 6.2, we want to learn how to find the regions between curves, namely the area of the regions between curves. Now we already know how to find the area between a curve and the x-axis. So let's perform an example of that. So for example 1, we want to say for each of the following, assume x and y are measured in centimeters. Sketch the enclosed region described by the following integrals. Decide whether to integrate with respect to x or respect to y to obtain the area. Draw a typical approximating rectangle and label its height and width and calculate the area of the region. So this is going to be a little bit of overkill for this particular problem because this particular problem is leading us somewhere. So I promise I'm heading somewhere with this madness. So I want to sketch the enclosed region described. So I have the cosine of x, and I'm looking from pi over 2 to 3 pi over 2, which is this region right here. So there's the enclosed region. No problems. Okay, so there's the enclosed region. Done. Now I want to decide whether or not I want to integrate with respect to x or respect to y. And honestly, this is a little bit out of order. I think it's better to kind of draw a rectangle and kind of think about it a little bit, but we can do it this way. So I've enclosed my region, and when I'm going to use a rectangle to find the area of that region, remember how we would stack those rectangles together with Riemann sums. Here, let me pause and remind you of Riemann sums. There it is. Remember, back in Calculus 1, we would use Riemann sums, i.e. approximating rectangles. We would stack them up and add them up. And then basically you let the number of rectangles get infinitesimally small. In other words, you let the number of rectangles, the width of the rectangles get infinite small. The number of rectangles goes to infinity. And lo and behold, the limit of the summation of those rectangles is the integral, right? So that's usually where integration comes from when you derive it in Calculus 1. So that's what we're talking about. We're going to take one of those rectangles, and you can imagine there's a whole bunch of them in here just kind of stacked up. Okay, so we are integrating with respect to x, right? Just like we are used to. So this is our graph of cosine of x. This is f of x, right? Our function. And then we are integrating, step 2, we are integrating with respect to x. X is our variable. And that's with respect to. Right? Or oh, I guess I should say to. There we go. All right, so we're integrating with respect to x. And you can tell because this little guy right here has a width. That width is delta x, right? It's the change in x, which of course, if we let the number of boxes go to, or the number of rectangles go to infinity, then that delta x turns into dx, right? As you let n go to infinity, right? So it's also known as the thickness. And again, we're heading somewhere with all of this. This is just a review of Calc 1 at this point, but I'm kind of breaking it down in a slightly different way than it was probably presented in Calc 1, but nevertheless, it's true. So it's kind of a different presentation of the same idea. Now, what is the height of this rectangle? The height would be the distance from 0 to the function, which in this case is just the function, right? It's also the length of that rectangle. So it would be f of x, which is cosine of x. Right, so this is the thickness, aka the width, which is delta x. Okay, so now I want to find that area. So this was step 3 right here. Step 1 is actually kind of shading it. And step 2 is integrating with respect to x. Step 3 right here is drawing a typical rectangle. Or part 3, I guess I should say. Part 4 is I want to find that area. Okay, so the integral from pi over 2 to 3 pi over 2 cosine of x dx is equal to the integral of cosine as sine. And we're going to take it from pi over 2 to 3 pi over 2. Oh, pi over 2, sorry, that's a 2. Which of course is sine of 3 pi over 2 minus the sine of pi over 2, which is negative 1 take away 1. right? Because on a unit circle, the sine of 3 pi over 2, 3 pi over 2 is down here. So its sine value is -1, and up here is pi over 2, and its sine value is 1. So it's -1 minus 1, which is -2. So that area that we shaded is -2. Oh, and if everything's in centimeters, if x and y are assumed to be in centimeters, then this would be centimeters squared. All right, no problem. We've done that a million times. It's kind of weird to think about drawing just one of the many rectangles that would be inside there, but we can manage it. And if you want to see a picture of those rectangles drawn, here you go. So here's the graph right here. And you can see that you can let that rectangle be anywhere on that graph. I mean, it's kind of wherever you want to think of it. It's everywhere and nowhere. And of course, if we let the number of rectangles increase, then the width of that rectangle will shrink. Good. Okay, so now we want to do it again in a slightly different way, because we want to integrate with respect to y. And we want to think about this a little bit for what this means. We're not used to doing this. I mean, we're told in Calc 1, you can do this with any variable, but we don't generally do it with any variable. We generally do it with x or t, which are usually the independent variable. But in this case, they want us to go from, now remember, because this is y over here, I'm just choosing my colors here. Because this is y for my differential, that means that these are y values. That differential tells us that these are y values. Y equals 1 is right here, and y equals 4 is right here. And so the enclosed region that I have to shade for part 1 would be between the y-axis and that curve, but also between the horizontal lines y equals 1 and y equals 4. So there's part 1. I have that region shaded. Part 2, we're obviously integrating with respect to y. I mean, you can see it's got y in there. So part 2 is pretty easy. It won't always stay this easy. We're heading to somewhere. So we're just trying to get you guys used to thinking of it this way. So we're integrating with respect to y, and that's why when I draw my rectangle, I'm going to draw a different kind of rectangle, a horizontal one instead of a vertical one. All right, now that rectangle has a width or thickness that's delta y, right? Because these are two little y values. Y equals something here and y equals something here. So it's change in y, aka delta y. And then the length of it is also the height, either way. And that would be g of y, which is equal to y squared plus 1. Okay. So then to find the area, oh, and I've already done the rectangle. That's over here. That's part 3 right there. So then to do the area, which is part 4 of the region, think about what this is. And I know it was given to you, but bear with me here. It's the integral from 1 to 4, and then it's rectangles that are stacked from 1 to 4. And so those rectangles have a length that's y squared plus 1 times the width dy. So it's length times width, stack them, right? Add them up. But of course they're infinitesimals because there's infinitely many of them, and that's why it's dy and an integral symbol rather than a sigma symbol. Come to think of it, I should have color-coded the previous page into, that's the width in orange, I changed it to orange, that's dx, and then that's the integrand, which is the height of the rectangle. So again, we've seen this before, but it's being presented in a slightly different way. This would be equal to 1/3 y cubed plus y from 1 to 4, which is equal to, oh, the real work here, 1/3 4 cubed plus 4 minus 1/3 times 1 cubed plus 1. which is 76 over 3 take away 4/3, which is 24. Oh, centimeters squared. Sorry. Everything was assumed to be in centimeters. So this would be centimeters squared because you're finding an area. And to look at the picture as well as to verify my math there, let me grab Desmos really quickly. Now Desmos is lovely because it'll let you graph in terms of y, something a calculator will not do. So I can just tell it, hey, g of y is y squared plus 1, and then I want you to shade it from 0 up until g of y between 1 and 4. And you can see the region that it's shading. And then the rectangle varies. So you can let the rectangle vary as you go. And then if you want to see the integral calculations, the integral from 1 to 4 of g of y is indeed 24. I was not wrong. There you have it.